These are the notes for 5, 6, and we're taking a look at kind of extending exponentials, and we had a kind of a question earlier in the homework where I think we were looking at population, and we were trying to find how many years it took the population to get over 1 million people. So it was something like, it started at 425,000, and I can't remember what it was growing at. It was growing at like 1.75% maybe, and then we had to figure out how many years. So we had to solve for up in the exponent, and this these notes today kind of address how do you actually go about solving that so that you don't have to guess and check anymore. So the context that we're going to kind of look at this skill in is this story about a math teacher, and she is, like math teachers do, she's thinking about math, and she thought it'd be really cool to have a function named after her. And so she came up with this function. And of course, all functions have patterns. So let's look for a pattern here. So she called her function the Gallus function. That's her last name. And looking at then the pattern here, can we figure out how the numbers in the pattern relate to one another? So if we look at this, we see a 2, an 8, and a 3, right? A 2, an 8, and a 3. Well, how do the 2 and the 8 and the 3 relate to each other? Well, let's see. We could do a whole bunch of adding and subtracting and multiplying and dividing, and we really can't get 2 and 8 and 3 to be related, right? 2 plus 3 is 5, so that doesn't work. 3 minus 2 is 1. 2 times 3 is 6. None of those work. But if we start looking, because we're looking at exponentials in this unit, if we start looking at powers, what we see is if we take 2 to the 3rd power, we get 8. So looking at this, maybe I should color code this a little bit. Maybe we say 2 to the 3rd power equals 8. So we're looking at tracking, here's the 8, here's the 2, and here is the 3. The 3 is green. Okay, there we go. So what it looks like is we've got this little subscript 2, and that becomes our, if we're familiar with the terminology, that becomes this big 2 here. We call that the base. So this is the base. And that's what the 2 is called in exponential terms. It's called the base. And of course 3 is the power. It shows up in the power spot. And then the 8 is just whatever answer you come up with from that exponential. So the 8 is, we would just call that the answer, the exponential answer, basically. I'm just going to call it the answer. The answer to that exponential question. So let's see if this holds true in the next one. The base is 5, and the power is 2, and the answer to that exponential is 25. So that pattern seems to work. Let's take a look at the next one. The base is 9, and the power is 1, and that answer to that exponential is 9. So that works. So there's the pattern. Let's just finish out this pattern here. The base here is 6, and the power here is 2, and the answer to that exponential is 36. So she's come up with a way we've come up with it. We've seen the pattern, I guess we could say, that kind of explains what her new function is all about. And so the nice thing to this pattern is kind of like we have, as I'll just bring the vocabulary up here, down here, we have a base, and we raise that base to a power, right? Write it in exponential form, and that gets us that answer. And so the nice thing is that the Gallus function, as she's described it here, if we wrote the Gallus function, Gallus to the base of the answer gives us the power. And so, like I said at the beginning of the notes back here, we want to be able to solve for the power instead of guessing and checking like we were doing a couple of sections ago. And so this Gallus pattern is a way to get the power and solve for that power. So, so let's kind of extend her pattern here. We don't know the base. So in these, we have a base to the second power equals a 100, the answer. So what base is that? That base is got to be 10, right? 10 squared is 100. Let's take a look at this next one. So this base is 3, and we don't know the power, so we'll put the power there. And I guess we'll call the power p. I'm going to hesitate to use the variable x. Let's call the power p. And that equals the answer. So we have the base 3 that equals the answer 27. 3 to what power is 27? So that power must be equal to 3. So let's take a look at applying this to this next one, Gallus of 6, of base 6 of 36. So we've got the base 6. We don't know the power again, but whatever power we need to equal 36. So that power then is 2, right? 6 squared is 36. And let's take a look at this last one. So now we have a base of 16, and we have a power of 2, and that is going to equal what answer here? What do we want to call the answer here? Well, let's just say answer right now. I'm specifically staying away from variables. We'll firm up the variables in a little bit. So 16 squared, whew, what is that? I think that's 256. So 256 is 16 squared. That's the answer. So this next question says, how can you turn the Gallus equation into an exponential equation? So if we have this relationship here, Gallus of base b of y equals x, then we know that we have that base, and we're going to raise that base to a power, and that is going to equal our answer. That's why I was staying away from x and y variables, just because I knew we were going to use those a little bit. So bringing back that vocabulary, then this is the base, and this is the exponent out here. That, and of course, when we're talking about exponentials, those are the components of an exponential expression, right? Is that it has a base and an exponent. So so that is the relationship then that relates this equation, this Gallus equation, back to an exponential expression. So as we can see then, it's this Gallus equation this Gallus function, whatever it does, it will take our base and our answer. It'll take our base and our answer, and it will enable us to solve for the power, right? So looking back at our, what I started the notes with, we have a base and an answer, right? Here is our base here from our homework assignment, and our answer would be the ratio between what we have left. We would have to do a little bit of math here, and I don't want to muddy the waters too much, but that we'd have to get that ratio, and then we could solve for the power directly if we use this Gallus function. So let's keep trying to fill in the blanks here for this pattern. So Gallus 2 of 1 equals what? So if you notice these next questions here, they have some commonality here. They all have an answer of 1, no matter what the base is. Okay, and so they're asking us, really what they're asking us is, we have a base of 2. What power do we need? Now I'm going to start calling this x. What power do we need? 2 to what power do we need to equal 1? That's what it's asking. And so, but without kind of going into what that answer is, you might know the answer already. Let's just look at the next one. The next one says 7 to what power equals, again, equals 1. And then this next one is saying 100 to what power, right? What power? This is my variable, and I am going to start to use x now for that power. Equals, again, equals 1. So you might have already, let's just finish off this last one. Well, let's not finish off that last one. Let's because that's generalizing, and we'll get to there in just a second. Let me just move this up a little bit. So so we know that whenever we take a number to a power and we get 1, that the power is equal to 0 in each one of these, right? 2 to the 0 power is 1, and 7 to the 0 power is 1, and 100 to the 0 power is 1. So in general, if we take a base, any base, and we want to raise it to a power, and we want to end up with an answer of 1, we know that that power is going to be 0. Okay. So that goes back to when we were talking about exponentials, right? Any base to a power of 0 is a value of 1. Okay, so let's take a look at another pattern. Now we're looking at the base 2 being raised to a power. So these are all being raised to a power here. It's the same type of question. We're being asked to find the power. And so we have 2 to a power, and now it equals itself. So 2 to what power equals 2? And the next one is 5 to what power equals 5? Those are the type of questions we're being asked now. And so we know that in order to get back the base, this power must be 1 and this power must be 1. So, and we can see that in the next one, that 100 to what power? 100, doesn't matter how big the number is, right? 100 to what power equals 100? And that power is still 1. So we knew this with powers anyway. So in general, we're just bringing back the connections here, that in general, when we take any base, right, doesn't matter what number it is, any base, and we raise it to a power, and we get that answer back, we get the base back, right? We get this base back. That exponent, that means we have a single value of that base. So we have a single power of that base. So these become what we call identities, right? Doesn't matter the bases, what the base is, we will always have those values for any base. Okay, so the general comment would be any base to a power of 1 is itself. In other words, the value of the base. So really what we're talking about here then, relating that Gallus pattern or equation to exponents, is we're talking about logarithms. That's really the name for it. It's not Gallus, it's called a log. And so if you notice the animation over here, the animation that's going over here, it's taking a logarithmic expression and converting it to its equivalent exponential expression. And you see how the base and the power and that answer all kind of rearrange. And so that's our first learning target, is that connection, that we have a way now to get that power out of the power spot and be able to solve for it. And we do that using logs. So, and in fact, we've talked about this earlier, that the log and the exponential are actually inverses of one another. So that's our first learning target. The first learning target is that this logarithmic function and exponential function are inverses. So think about that. You know, it's kind of like how we solve in general, right? We undo things. We undo addition with subtraction, multiplication with division. We undo powers with logs. So we have a base to a power of x gets us our answer, and the inverse of that is a log to the base b of that answer gets us our power. That's how we are able to get that power. And so just to recognize that is a solution method to solve for that power. So we can solve for the power x. Our other learning target, I guess that's learning target 1. Our other learning target is to evaluate logs. I'm going to call it learning target 3 just because in the notes I'm looking at it says 3. This is actually learning target 1 and 2 apparently. I'm not quite sure why. But so this learning target 3 is evaluating. So that learning target 3 then is focused on the relationship. For example, I'll pick one out of the homework. Will log base 2 of 8 equals 3? And so a lot of times we need a calculator. We can easily see that 2 to the third power equals 8, but sometimes we need a calculator for those, and we'll get into that. Doing that as we go through the rest of this unit. But I also want to mention, when we're evaluating, we have some logarithmic buttons on our calculator, and I just want you to be familiar with them. They're called common logs, and I think they're called common logs just because we use them a lot. But LOG, when we just say LOG, it implies that it's log base 10. So we're counting by powers of 10. 10 to the first power, 10 to the second power, so the base is 10, when you just see log without something written next to it. And log base e, so if we would write it like this, log base e, we call the natural log. Let me reverse actually that so that it's a little more consistent. We have this thing called a natural log, and that's the log of base e. E is a number, kind of like pi. It's about 2.71 roughly. You actually have a key to find out its exact value on your calculator. In Graph and Calc, it's the key that is just below the pi key on your Graph and Calc. So it's about 2.718 roughly. And so those are the two common logs that we have in our calculators and that we use to calculate values. And then the last learning target, which is learning target 4, is solving equations. So this involves the rearranging. This involves the rearranging that we do with the exponential expression. So, and just a quick caveat also is that if we have a log of any base, and we can rewrite the answer here as the same base to a power, then that just equals the power. So you got so we can kind of use that to help us shorten the solution process, and then likewise, if we have any base raised to a log power with the same base of a number, that also just equals the number. And so those are handy things, handy patterns to use, as well as this pattern that rearranges our logarithmic expression to an exponential expression and vice versa. So, you know, as you do the check your understanding, I just kind of want to preface this. This is going to be a rearrange. So we want to solve for the power of x. We could guess and check, but really what we need to do is we need to rearrange this in its logarithmic form. So this is log, the base is 2 of 31.6 equals x. Okay, and so this is where your calculator comes into play, because this is actually a decimal, right? We're saying 2 to what power is 31.6, right? And we could guess and check, but just in practical use here, the way we get this answer is we use our calculator. Okay, so we're going to calculate, this. And the way we calculate this is we say because we don't have a base 2 key, the way we change that is we say the log of 31.6 divided by the log of 2. So on your calculator, it would be the log of, 31.6 divided by the log of 2. And that answer is roughly 4.982. So 4.982 is the power that we have to raise 2 to get 31.6. So let's try that. 2 to the 4.981852653 power. The way I'm going to enter that is I'm not going to enter the decimals, all the digits. I'm going to do a second key and an entry key. Oops, clear. I said that wrong. I'm going to raise that to a power, I'm going to do a second and answer key. It's next to enter. second answer, it says A and S, and that A and S takes whatever answer is right above it, so it's the 4.98. And then if I hit enter, you can see I get that 31.6. So we call this the change of base, and I would almost consider that a learning target in itself. So we're changing the base from 2 to 10 when we do that sort of calculation. And so you will do that then for B and try that on your own. When we rewrite this next one, we can say log base E of 7.8 equals x. But log base E is natural log, so we have a key for log base E. It's it is an ln key, and it's just beneath the log key. It's right here. And we can solve it like that. And that's kind of nice, because then we don't have to do the division process. But we could do this, and you go ahead and try this as you're going through your check your understanding. You can also do log of 7.8 over log of E. Okay, remember we have that number E, it's the division sign. You could do that and get the answer. So that's kind of another way, but log base E is natural log. So this one, the way we solve for x is we rewrite it. We have 3 to the 4th power equals the answer, and the answer is 2x minus 5. So once we have 3 to the 4th power, we can get that number, we can go ahead and solve for y. So I'm going to let you finish that solving. And then we're a couple of applications here. It says an initial deposit of $200 is invested at 6.5 interest, compounded annually. So we're going back to these annual equations, and it says how long will it take to grow to 400. So this is like what we started the notes with, right? And so when we set this up, we're going to be using that y equals a, let's see, this is growth, so it's 1 plus r to the t. We're solving for t, that's the question, right? We got the how long. Oops. That's the t. And so let's see, we got 400 here, and this is 200, 1 plus 0.065 to the t. And so in order to do a solution like this, let's go back to the color coding. This is the base, right, this whole thing. It's the 1.065. Hold on, let me write my 0 more neatly. There we go. And of course, this is the power here. And so I need my answer. My answer is not, I was alluding to this a little earlier, my answer is going to be dividing out the 200 first. So we actually have to do that as a first step. I don't need my calculator anymore. In order to get this to be able to be written as a log, we actually have to take this. Let me duplicate this. We actually have to take this and divide by 200 first. In other words, we've got to isolate the base. So this is 2 equal 1.065 to the t. Okay. Now that we've isolated the base, so this is, let me just do a little annotation here. I've isolated the base. Okay. Now we can rewrite it in log form. So now we have log of 1.065 of 2 equals t. And now we can put that into our calculator using that log, the change of base form. So now we can go ahead and say log of 2 divided by log of 1.065 equals t, and we can find out what t is. So I'm going to let you go ahead and calculate that and see if you can match it up with the answer. And then you're going to use that process down below with the iPhone question, but we're going to do a decrease. Okay, which means you're going to change that to a minus sign. So go ahead and finish that, check your understanding, and then you will have similar problems here